I'll just start right now. My name is Beydler, and if you don't know me, I'm a math professor here at Mount Sac. Being a professor, I probably over-prepared this a little too much. Long time ago, in a galaxy far, far away, you learned how to add fractions, right? There was the right way to add fractions. Find an LCD, scale the fractions up, and just add across the top. There's the right way to add fractions. And there's the wrong way to add fractions. This wrong way is sometimes called the freshman sum because for freshmen in high school, or college, or sometimes grad school, it's a common mistake. But I think it's a really neat mistake, and I'll explain why. Notice that 3/5 is in between 1/2 and 2/3. In other words, for these two fractions, if you add the tops and you add the bottoms, you get a fraction that's in between. If you're not convinced, you can just convert these fractions into decimals, and you'll see that the number is in between. It's 0.6 right here. Now, wait a minute. This has got to be a fluke, right? This is just some example that I picked out to try to fool you guys. Let's try some other examples that I picked out. So we add the tops to get 6. Add the bottoms to get 12. 6 over 12 is 1/2. That's the fraction that's in between. And if you don't believe it, look at the decimals. All right, let's try another one, hand-picked. Add the tops to get 15. Add the bottoms to get 19.
I don't believe it.
But it's true. All right, what about negative numbers? Aha, here we go. Add the tops to get -3. Add the bottoms to get 8. It's still between. One positive, one negative. Add the tops, -3. Add the bottoms, 13. Still between. Improper fractions. Add the tops, 8. Add the bottoms, 6. Between. Now at this point, a scientist or engineer would say, aha! When you add the tops and the bottoms of fractions, you always get a fraction that's in between. To which a cool mathematician would say, yeah, prove it. And that's exactly what we're going to do. There's nothing against scientists or engineers. We're going to start with an algebraic proof, and to make sure that we're in the right frame of mind, the mathematical mindset, we'll start with the traditional whiff of the marker. Yes. Okay, I think we're ready. Okay. And we'll present our claim or our theorem in this way. Suppose you've got these two fractions. We'll call them a over b and c over d, such that a over b is the smaller of these two fractions. We can do that without loss of generality because if we've got, well, two different fractions at least, one of them's got to be smaller. Why not call it a over b? What we're going to try to show is that if you add the tops, a plus c, add the bottoms, b plus d, that you get a fraction that's in between the original two. You might be wondering, well, what if the fractions were the same? And let's address that in a little box on the side right here. If the fractions were the same, well then if one of them would be a over b, one of them is a over b, the other one has to be a over b. So if we add the tops, we would get a plus a, add the bottoms, b plus b, 2a on top, 2b on the bottom. We can reduce this fraction down by dividing top and bottom by 2. And we get a over b, which was the same as the fractions that we started with. So in a sense, if you allow for equality in your inequalities, then this a over b, this result, is sort of between the original two fractions. So this is the case when the fractions are the same, but the much more interesting case is when you have two fractions that are different. All right, so we'll start our proof. All right, suppose. Erase that. Suppose that a over b is less than c over d. And we're going to make two other assumptions. One is that b is positive, and the other is that d is positive. So in other words, that both the denominators are positive. Notice that we can still handle any pair of fractions that you want to propose, because if one of the denominators is not positive, well, we can make it positive by multiplying the top and bottom through by -1. If you really want to check the cases where b is negative or d is negative, you can actually do those cases as well, and it'll work out. If we did a rigorous proof, we'd probably want to do that. But for this one, we're just going to suppose that both b and d are positive, and not lose too much in the process. The rest of the proof will break into two steps. So step number 1, we're going to show this inequality right here, that a over b is less than a plus c over b plus d. The second step will be the other inequality. That a plus c over b plus d is less than c over d. So here we're just taking this compound inequality and breaking it into its two parts. We're going to prove each one of those. All right. So in the first step, the only thing we really have to start with is our main assumption that a over b is less than c over d. So we'll start there. We'll start with our assumption. A over b is less than c over d. And now what we're going to do is clear out all the fractions by multiplying both sides through by the LCD, which in this case is BD. Or if you like, multiply the B to the right, multiply the D to the left, and you'll end up with AD is less than BC. All right. Notice that we didn't have to flip the inequality direction because we assumed B and D were positive. If you multiply by a positive number, you don't have to flip the inequality direction. Now the next step here is going to seem a little bit mysterious, a little bit magical. What we're going to do is add AB to both sides. We'll explain why we're doing that in just a few moments. We're adding AB to both sides. Seems a little bit magical here. Then we'll factor out an A from the left, factor out a B from the right, and we're almost there. Divide the B to the left, divide the B plus D to the right, and we've got A over B is less than A plus C over B plus D, which shows our step.
How do you know the inequality doesn't split?
How do you know the inequality doesn't split?
Flip.
Oh, it doesn't split because of the, well, the B and the D are positive, so B plus D is positive, so you divide it over and it's still positive. Yeah, thanks for the question. And then divide both sides by B, but B is positive, so that's okay as well. Yep, thanks. Okay, now let's go back to this adding the A plus AB business. I mean, that seemed like a magical step. How did I know to add AB to both sides? Well, honestly, I didn't. In fact, when I was at home, and no one was looking, that's not a good sentence, but and no one was looking, I actually started from what I was assuming, or started from what I was trying to show, and worked backwards through the proof towards my assumption. So I started with what I was trying to show in step number 1 and worked backwards through the proof to get back up to my assumption. And then I turned around and wrote the proof forwards for you. Makes me look pretty clever, huh? So in fact, I wasn't adding an AB to both sides. I was canceling the AB off. It was simplification, not magic. All these steps were just simplification. Okay, so step number 2 here is pretty much the same thing. So we have a over b is less than c over d. That's our assumption that we start out with. Multiply to clear the fractions out. The magical thing to add here is cd. Just add that right here. Factor out a d from the left. Factor out a c from the right. Divide the d to the right, divide the bd to the left, and we've got a plus c over b plus d is less than c over d, which is what we were trying to show for that step. Okay. Again, no division by any negative numbers or multiplication by any negative numbers, so we're safe. So let's bring this all together, steps 1 and 2. So since step number 1 was true, and step number 2 was true, we know that when we add the tops and add the bottoms, we get a fraction that's in between. Yep. And we'll end the proof with a little QED. You know, if you don't know QED, it's Latin for quod erat demonstrandum, which means that which had to be demonstrated. In other words, that's what we set out to prove, and we proved it. It's a nice way to signal the end of your proof. Right, so that's an algebraic proof, and it works. It's not exciting, but it works. There is, however, another way, a way that you can see why our claim is true. Now, I have to warn you, your eyeballs may pop out of their sockets, but don't worry, I'm here to catch them. Here we go. I was up late running this, so got kind of silly. We'll start by making a coordinate system. And in that coordinate system, we're going to create a vector, b comma a. So that the x component is b and the y component is a. We'll make another vector, d comma c. The x component is d, the y component is c. Now one thing you know if you've taken trig or beyond is how to add two vectors that are tail to tail like this. What do? You make a parallelogram. Yep. So you make a parallelogram, and the sum of these two vectors runs diagonally across the parallelogram, just like this. But we also have the vectors in component form. And so to get the sum in component form, we would just add the x components, b plus d, add the y components, a plus c, and now we've got the sum in component form. Now, what we're going to do is look at the lines going through these vectors. We're going to look at the slopes of the lines going through each of these vectors, starting with the bottom vector. So if we want to figure out the slope of the line going through this vector, well, we can do a rise over run from the tail of the vector to the tip of the vector. The rise is a, the run is b. Rise over run gives you a over b, and that's the slope of the line going through that vector. Let's look at the slope of the line going through this vector. Here the rise is c, the run is d. Rise over run gives you c over d, and there's the slope of the line going through that vector. And it's the same thing for this blue vector in between, the summation. The rise is a plus c, the run is b plus d. Rise over run gives you a plus c over b plus d. So, just by looking at the picture and knowing how vector addition works, you can visually see that the slope of the line going through this vector is between the slopes of the lines going through these vectors. And that proves our claim. Quite easily done. Thank you for listening.